Okay, so I'm going to do a combo of what's covered in chapters 24 and 25 of the text. Although I won't be following the textbook closely here. So it's going to be mostly showing pictures and talking about them. So if you have questions or want me to slow down so you can write stuff or whatever, just let me know. But galaxies is what we're going to talk about. Cities of stars, as it were. Our sun is one of something like, and the estimates have changed over time, it's something like about 400 billion stars in our galaxy. I think I've mentioned before that people often don't understand the scale. People will confuse, not you, people will confuse things like solar system versus galaxy and so forth. And it's important to not confuse those things. I like to make scale models. I'm all about scale models. So if you make a scale model where the astronomical unit, the distance Earth from the sun, okay, the semi-major axis of orbit around the sun, but that's basically the distance of the Earth from the sun because our orbit's nearly circular. If you call that 2 millimeters, right, 2 of the smallest divisions on this meter stick here, then our galaxy would be, to that same scale, the size of the actual planet Earth. The disk of our galaxy would be that large if the distance from the Earth to the sun was 2 millimeters. So galaxy much, much bigger than solar system. And we're just one star amongst many in our galaxy. So here's an artist's conception of our Milky Way galaxy as viewed from the outside. And by the way, the word galaxy comes from the Greek word for milk. And so Milky Way, galaxy, those are certainly related terms. Because if you go outside at night, well, not in the city of Delaware, sort of in Perkins, more if you're in a rural area, you can actually see the band, the Milky Band, if you will, of the Milky Way stretching across the sky. And that's the disk of our galaxy seen from the outside. Seen from the inside. We don't have any photographs of our galaxy from the outside because, well, you'd have to go at least tens of thousands of light years to do that. And this is beyond current technology. And even if it weren't, okay guys, go get those photographs for us. Well, you know, tens of thousands of years later, here they are! Future generations or the AGIs or whatever we did to send on this mission. Anyway, from within the galaxy, we do observations that give us a sense of its structure. And so here's an artist's conception of the Milky Way viewed from the outside. We live in a spiral galaxy. It has, as we'll see some photographs later, which show other spiral galaxies. We saw M83 when we were talking about the interstellar medium, has spiral arms. It has a spiral structure to it. It looks like a pinwheel, if you will. And so here is a conception of the disk as seen from above. Here are the spiral arms. In the middle is what we call the central bulge. The spiral arms are bluish in color. The central bulge is reddish in color. And it sticks up above and below. Not that there's intrinsically above and below, but on either side of the disk of the galaxy, where the sun lives. And the reason for the blue color of the disk of the galaxy is because it's a region of, it's a place where there's active star formation. So what very luminous blue stars are we talking about that would be giving the galaxy its blue color? They're very rare, but they're also very luminous. And so overall, they kind of dominate the light of the disk, even though they're not a significant fraction of the total population of stars. What kind of stars are those? What are their spectral types? O and also you could add B to that. So hot, young O and B type stars being born in the spiral arms give it the bluish color. In the bulge, that's not a region of active star formation. The gas and dust has pretty much been used up there. And so the most luminous stars in the bulge are going to be what kind of stars? It won't be O and B type stars because they only live a few million years. and the galaxy is billions of years old. So what's going to dominate the light of the bulge? What's the most luminous stars you'll have if all you got left is low-mass stars? Not white dwarfs. Those are they're in there for sure. But remember, white dwarfs are very dim because they're small. They're hot, but they're also small. And these stars, we want them to be reddish in color. So what's the basic idea here?
Red giant.
Red giants, yeah. Low-mass red giants dominate the light of the central bulge. And so here's an artist's conception of an edge-on view of the Milky Way. So it's a disk. If you're above the disk, you can see this pinwheel, the spiral. If you look in the plane of the disk, then you get an edge-on view like this. The disk of our galaxy is about 100,000 light years across, or about 30 kiloparsecs across, which is the units that astronomers typically use as parsecs and kiloparsecs rather than light years. But of course, 100,000 light years means that it would take light 100,000 years to cross from one side to the other. And the disk itself is quite thin compared to its diameter. So we're talking about like 1,000 light years or so is where most of the material in the disk lies. The sun is a star within the disk of our galaxy. It's a population 1 star, Pop 1, Roman numeral 1, population 1 stars live in the disk. And then we have surrounding the disk the halo of the galaxy, which is more of a spherical overall distribution of stars. And there are quote-unquote field stars in the halo. So those are just isolated individual stars that live there. And then also there are numerous globular clusters in the halo of our galaxy. Well, yes? No, I'm not. I'm just using camera sound because Reese said that the video from Friday cut out after a few minutes. So I'm not. I have to test that mic, so I'm not trusting it. So yes, thank you for asking. I'm using camera sound. I'll have to process the video to boost the level, but that's okay. That's not hard to do. So won't be quite the audio quality, but it'll get the job done. Yep. Alrighty. So globular clusters and field stars live in the halo, and they systematically have lower metallicities than the disk stars do. They are much older. If you make HR diagrams of globular clusters, they're all billions of years old. And so systematically, the halo stars are older than the disk stars. There's no active star formation in the halo, but there is within the disk. And so that's why the halo stars are much more metal poor, because there wasn't enough time for significant metallicity to build up. The metallicity, of course, when we talk about metals in astronomy, what are we talking about? Yeah, okay, let me rephrase that. When we talk about metals in astronomy, what are we not talking about? Hydrogen and helium. Metals are everything else, right? To an astronomer, carbon is a metal, oxygen's a metal, iron's a metal too, but we just generically use the term metals for anything that ain't hydrogen and ain't helium. Okay, what questions do you have at this point? Can I push the magic button to go on to the next slide? Alrighty. So here's a representation of how stars move within the galaxy. They've exaggerated the up and down motion of stars within the disk to make it easier to see, but within the disk, stars follow nearly circular orbits around the center of the galaxy, and it's systematic. In other words, the stars in the disk are essentially all going around in the same direction, just like all the planets go in the same direction around the sun in their orbits, but they also bob up and down. So disk stars orbit in circles. It's not quite circles, as we'll see in a minute, with the same orientation, except for a little bit of up and down motion. So the sun does that as well. Sometimes it's above the disk of the galaxy, sometimes it's below the disk of the galaxy. I should really say sometimes it's on one side, sometimes it's on the other side, because there's no up or down in space. So it doesn't really intrinsically mean anything to say above and below, but it bobs up and down on either side of the galaxy. And you'll joyfully do a homework problem about that, where you'll show that you can make a model where the vertical, if you will, the perpendicular disk to the disk motion of the sun is essentially simple harmonic motion. And what you'll do is use Gauss's law, but you'll use it for gravity instead of saying, yeah, gravity is GR, right? Well, now we're going to switch back to Newton for this, because often it's more convenient to do the Newtonian calculation. If you had a sheet of charge, or some sheet of charge with some thickness, then you could use Gauss's law to figure out the electric field within the sheet, right? You can do the same thing with Newton's law. You can use Gauss's law for gravity, because fundamentally, Gauss's law comes from the inverse square law nature of Coulomb's law, and mathematically, Newton's law of gravity looks exactly like Coulomb's law, right? It's a 1/r² force, so you can use Gauss's law for gravity, and so you can make a Gaussian soup can and figure out what the gravitational field should be as a function of position above and below the plane, and you'll have fun doing that problem and estimating the sun's period of vertical oscillations and so forth. I can't tell if you believe me. I'm sure you believe me. It's going to be fun, right? Yes, it's going to be great. Okay. So in other words, the stars in the disk are kind of like blah, 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 as they go around. It's a merry-go-round. We're on the galactic merry-go-round. The halo stars are not so organized. The halo stars orbit every which way. The disk stars have a net angular momentum because they're all going around the same direction. The halo doesn't have much net angular momentum because there are stars going at every orientation and either direction in their orbits. And so their angular momentum doesn't add up to much. So halo stars travel high above and below the disk on orbits with random orientations. And bulge stars also have orbits with random orientations. Okay? Questions, comments, observations? And have you noted that the disk stars are population Roman numeral 1, high metallicity stars, and the bulge stars, and the halo stars are population Roman numeral 2, lower metallicity stars, and systematically ordered. Yes?
I understand the stars that are in halo would not follow a systematic direction, but the bulge stars are closer to the center, so why would they go around and around?
So it's going to, it's going to have to be related to how the galaxy formed. And so we'll talk a bit about galaxy formation models for spiral galaxies later. But the idea is basically that overall, when you think of star formation, right? A large cloud initially isn't spinning very much, but it does have angular momentum, and so as it shrinks, it starts to exhibit more rotation because of conservation of angular momentum as it's shrinking. And so it would seem that the disk formed later than the halo, and so it has a more systematic rotation to it than the halo does as a result of that. So halo stars would have formed before a disk had formed and settled out. Question, yes?
So with some of the stars having more of a random orbit, does does that ever like mess with any gravitational like balancing? Does the things kind of get pulled out of whack sometimes?
So the thing is, you have to remember just how far apart stars are compared to their sizes. If the sun was a tennis ball, the nearest star, like if the sun's a tennis ball in Columbus, the nearest, the typical separation between stars is there are other tennis balls that are like, the nearest ones are like in Chicago from here, kind of distances. And so close encounters between stars are pretty rare as a result of that. And so the answer is overall, no, not particularly. The stars don't particularly distort one another's orbits too much because they're generally very far apart from one another compared to their sizes. Halo stars sometimes are also called high velocity stars because we're here in the disk and everything's kind of moving around systematically. So the speed of stars in the disk nearby us relative to the sun isn't that large because the sun and those stars are all orbiting the disk in the same direction. So it's like a bunch of traffic going down the road and the cars are moving at comparable speeds, right? When you're going down the highway, why, you might be driving 65 miles per hour, but the other stars around you also are. And so relative to you, they're not moving very fast. You're catching up to some, you're leaving others in the dust, but very slowly. But the halo stars are coming in at all angles to the disk. And in particular, that means, you know, imagine that, oh, I'm driving on the highway and the cars I'm going the same direction as, I'm not moving very fast relative to them. But now there's a, well, planes move faster than cars, but imagine there's a rocket or something, I don't know, that's coming down at around 65 miles an hour, like everything else. Well, its speed relative to you is going to be closer to that full 65 miles an hour because it's moving perpendicular to the direction that you're going. And so the stars in the halo, when they're crossing through the disk, the ones that are in our vicinity because they're passing through the disk, have systematically higher velocities relative to the sun because their velocity vectors are more nearly, are at bigger angles to the sun's motion. Does that make sense? So there's high velocity stars as well. Okay. Can I push the magic button? Okay. All right. So here is a lovely, beautiful spiral galaxy. It is M51, the Whirlpool Galaxy, and you can see how it got that name. It actually has a companion as well, and the gravity from the companion, they had a close encounter, probably helped excite the spiral arm density waves we'll talk about in M51. So it's M51, that means it's number 51 on Charles Messier's list of things that are not comets. Yes, it's definitely not a comet. Excuse me. Okay, so you can very distinctly see the spiral arms. You can see their bluish color from the hot O&B stars that are born there. You can see these pink regions right here. What are those? They're H2 regions, right? Regions of active star formation. They are lit up by the ultraviolet light from hot, young O&B type stars that have been born within them, ionizing the hydrogen gas within them. And then remember, when electrons recombine with protons to reform hydrogen atoms, they'll drop down the energy ladder. And ones that transition from some higher energy state down to n equals 2, why those produce emission lines that are in the, whose series is that? The visible spectral lines? The Balmer series spectral lines, right? And for hydrogen, what are the colors of the lines? N equals 3 to N equals 2, it's a beautiful what color? Remember? That's the longest wavelength one, N equals 3 to N equals 2. The overall color is pinkish, but it's a blend of 4 visible spectral lines. The longest wavelength one, hydrogen alpha, H alpha, is a lovely, yes, red color. You're wearing a hydrogen alpha shirt here, okay? Not really, but okay. And then hydrogen beta, n equals 4, n equals 2, is a lovely, starts with a T. Teal or turquoise, you might say. And then there's n equals 5 to 2 and 6 to 2, which are bluish purple. Some might, at some risk to their personal safety, call them indigo, yes. Okay, calm down. I don't have to. Indigo. Those blend to form the pink color, right? And so here, dark patches on the inner edge of a spiral arm show where gas clouds are packing together. We'll see why they're packing together in a minute. Packing together, and compression of these clouds, because they're colliding with one another and their magnetic fields help with that, help with compacting them. Compression of these clouds triggers star formation in the arm. Blue specks are young stars that formed in the spiral arm. Of course, it's a speck in the photo. If you were close to it, you'd be like, wow, look at that big star. It's like 10 times bigger in diameter than the sun. But from millions of light years away, blue specks, red patches are ionization nebulae allowing the hottest, youngest stars. The point of this is going to be that spiral arms are density waves that travel through the, I really can't touch the cord, that travel through the disk of the galaxy. So in other words, unlike Vegas, where what happens in Vegas stays in Vegas, not so with the spiral arms. Things don't stay in spiral arms. They move through the spiral arms because the stars, gas, and dust are orbiting the galaxy at a different speed than those density waves are traveling around the galaxy. And so typically stars will catch up to and pass through spiral arms. Our sun takes about 225 million years to go once around the center of our galaxy. And so it has passed into and out of spiral arms throughout its existence is what it comes down to. And one thing I forgot to mention here, here's the sun's location. We're out in the suburbs. We're about 27,000 light years away from the center. We're about 8 kiloparsecs away from the center. If you looked at a photograph of the Milky Way from the outside, the sun would look like it's near the periphery of the disk because the stuff gets less and less, the normal matter is less and less concentrated the farther you are from the center. So the sun would kind of look like even more so that it's kind of in the outskirts, basically, of our galaxy. Okay. So we have what's called the winding problem. It's not a genuine problem because we know the solution to it. But you might imagine, well, what if spiral arms were made of material that stayed in the spiral arms? That's what I call like a material spiral arm as opposed to what they really are, waves that are traveling through the disk. If the material in a spiral arm stayed in the spiral arm, well, here's the problem. So it turns out, we will see, that orbital speed is nearly independent of distance from the center once you're away from the galactic bulge. So everything is going around the center at about the same linear speed. But on the other hand, well, that means that stuff closer to the center will take less time to go around the galaxy because the circumference of the circle is smaller if you're closer to the center. So, yeah, here's two things. They're both moving the same speed, but the one closer to the center makes it around quicker, right? It's just like if you had a bunch of runners on a track, a circular track, it wouldn't be a very fair race if you didn't account for the fact that the people on the inside don't have as far to run. Even if they're all running the same speed, the people on the inside are going to finish a lot quicker. Yay, good job! You drew the inner track, right? Well, it's kind of like that with stars around the galaxy as well. So the winding problem was, if the material in spiral arms stayed in them, then the spiral arms would wind up over time such that by the current age of the universe, the time scale would be such that they would be much more tightly wound than we actually observe. So imagine that you have 4 stars, A, B, C, D, or gas clouds or whatever, along a spiral arm, which, just for convenience, we started up straight. Well, at first you might think, well, oh, this explains the spiral structure because they're all going the same speed, but on the other hand, the ones that are further from the center, they'll have traveled the same distance in their orbits, but that's a smaller angle that they'll have traveled around the center. And so star A is getting out ahead in terms of angle. It's already gone around 180 degrees. Star B, twice as far away, has only made 90 degrees in the orbit. Star C, maybe 3 times as far away, it's like 60 degrees, and so on and so forth. So this would initially look like, oh, it's explaining the spiral structure. Things are just kind of being wound into a pinwheel. But given the time scales involved in the age of the galaxy, I mean, even the sun out near the periphery is taking like 225 million years to go around once. How old is the universe, roughly?
14 billion?
Yeah, roughly 13.8 billion years old, 14 billion years old. So, okay, we're, just rough estimate here. How many times does the sun go around the galaxy in a billion years? If it takes 225 billion years to go around once, yeah, about 4 times. The sun goes around the galaxy about 4 times in a billion years. And it's only about 10 billion years old, but imagine a star that's been here since the start. Well, okay, if the galaxy's, say, 12 billion years old, because galaxies took some time to form right after the Big Bang. Say a galaxy's 12 billion years old. Well, if a star is going around the center 4 times every billion years, that would be 48 times around the center for stuff at the periphery and in our Milky Way, and even more so at the center. So there's no way this could be what's happening in the Milky Way. The spiral arms would be totally wound up way tighter than this. So this is not what's going on with spiral arms. But that's the winding problem, per se. It's only a problem if you think this is how spiral arms form. They don't. What questions do you have? Yes?
Could you explain it again, please?
From the beginning?
The last few sentences where you said that this is not how it goes.
Yeah, this isn't what's happening, right? In other words, when we look at this galaxy right here, right, see about how windy it is, right? The spiral arms would be more like this if material in spiral arms stayed in them. If spiral arms consisted of definite batches of material that were always in the spiral arm, then because of this, given how long it takes stuff to go around the center of the galaxy versus how old galaxies are, everything would have gone around many, many times. It would have been wound up very, very tight by this point in the history of the universe. That's the winding problem. Again, it's not a problem in that we know the solution to it, but if your hypothesis is what's in a spiral arm stays there, spiral arms, the stuff in a spiral arm is always in a spiral arm, they would have gotten wound up way too tight by now. Does that make sense? That's the idea with the winding problem. Okay? Can I push the magic button? All right. So here is the solution. All right, so you gotta visualize here. I wish I had an animation of this. So don't hesitate to ask me if you're having trouble visualizing what's going on here. So in the textbook, if you're curious enough, you can read about, they developed a mathematical model that shows how this arises. But I'm just going to qualitatively describe it here, because if I'm going to choose, I want to spend more time on cosmology than going through the math of this. Although, when I post my lecture notes, you'll see I also develop it in my lecture notes. And it's very, very interesting, and so I'm certainly not discouraging you from looking it over, but I'm going to tell you what the result is. Okay, so spiral arms are actually density waves that travel around the disk at a different rate than the stars and the ISM. What's ISM stand for? So interstellar medium, yeah, but gas and dust. Thus, the winding problem doesn't arise because, a wave can be something that just is traveling around and keeping its shape, essentially, because it's a different sort of beast. And so, turns out that really the orbits are not circles. They have an oval shape. It's not quite an ellipse either. It's not an ellipse, but they have characteristically an oval shape. And it's really kind of fun because if you know anything about Ptolemy's representation of planets orbiting the Earth, so to speak, right, in his model, there's epicycles and deference, where you have the motion of the planet is on a small circle called an epicycle that is centered on a point that moves on a larger cycle called the deferent, okay? And it turns out that when you make this model, if you see it in the book, you do that. You have an epicycle, you take the circular orbit, which would be the unperturbed orbit, and then you can say, okay, but then the star moves inside and outside that orbit, and you can model it as an epicycle. Ptolemy strikes again, but the end result of it, and so, in Ptolemy's model, if something was going around the epicycle fast enough, you'd get kind of a loopy-loopy-loopy kind of thing like that. But on the other hand, if it, say, goes around the epicycle twice every orbit, well, then instead of getting loopy-loopy-loop, what happens is sometimes it's a little closer to the center, sometimes a little farther from the center, and you put it all together, and it's basically like, it looks a lot like an ellipse. It looks like an oval in the end. So, here's oval stellar orbits with their major axes aligned. And what's happening is that the different parts of the disk are perturbing one another. There's gravitational perturbation from different parts of the disk. Imagine that the orbits had their major axes aligned. Well, there's no spiral pattern here. It's just ovals with their major axes aligned. I don't know what else to call it. But this kind of pattern could produce the bar and the barred spiral. Well, we'll see what a barred spiral is in a second, so we don't have to worry about that right now. But one can show, see the text or my notes for these chapters, that the system is unstable to perturbations. There's a natural tendency to, if you kind of jiggle the system a little bit, for this to happen. If the major axes are systematically inclined to one another, in other words, if I go from one oval to the next, the long axis keeps shifting direction the further out you go. If they're systematically inclined to one another, from the center to the edge of a galaxy, look at that. Do you see the spiral? Ooh, it's a spiral pattern. Okay, now here's where I hope you can visualize what I'm going to be talking about here. Okay, so what we're showing here, we imagine that this pattern is just sitting there. In other words, we're in a frame of reference that is co-rotating with the spiral arms. We are in a frame of reference where really the spiral arms are going around the center of the galaxy. But if you adopt a frame of reference that is spinning at the same rate of as the spiral arms is, they'll look frozen in place in that frame of reference. So that's my first question is, can you visualize what I'm saying there? If you are spinning around at the same rate the spiral arms are, you'll see them locked in place. Kind of like, imagine that I put this on the ground on a turntable and it is spinning around and I do this while I'm looking down on it. Well, relative to me, if I have my arms, say, along one of those long axes, if I'm twirling around at the same rate as the whole pattern is, my arms are always along that long axis. So if I made a video with the camera right here, everything would just look locked in place as a result of that. Yes?
Is it kind of like an interstellar and we have to walk on?
Oh my God. I don't remember. So Interstellar, when they did what?
They're trying to like attach their ship
To the one that's moving us.
Oh, yeah, so you'd have to spin at the same rate in order to do that, yeah. Or in the movie 2001, for example, right? So if you had a spinning space station, which you would do in order to make artificial gravity, if you want to dock with that space station, then you want your ship to be spinning at the same angular rate as the station is. And so what you'll see in your spinning ship is the station just looks like it's locked in place for you. Yes. Yep. Okay. So here we're showing them in a frame rotating at what's called the global angular pattern speed, capital omega sub GP. Capital omega here means the angular rotation rate of the whole frame, right? So in other words, what are the units for angular rotation? Well, could be various things, but if you use radians, if you're, oh, I'm in mechanics and I'm studying torque and angular momentum and all that kind of stuff, right? L equals I omega. What are the units of omega? So it's radians per second. Yeah. How many radians it's spinning around per second? Right. So this has units of radians per unit time. In SI, it'd be radians per second. Okay. If a galaxy, this is going to take like, I don't know, 100 billion years to go around once. So this would be a very small number in terms of radians per second. But that's what the SI units would be. But you might decide, no, I'm going to make it radians per billion years, radians per gigayear or something like that, and then you get a more reasonable number. But in any case, in this frame, the density wave is stationary. In an inertial frame, the whole pattern constituting the density wave rotates with the global angular pattern speed, omega GP. So in other words, now let's not be in that non-inertial rotating frame and just watch this spin. Well, imagine I cut this out and I take it and I start going like this. I'm now spinning it at the global angular pattern speed, omega GP. And why do you see in your mind the spiral arms moving around the center of the galaxy, right? So that's what's happening in an inertial frame, right? If you're just drifting there deep in space, watching the galaxy from the outside. And boy, are you ever good at making time-lapse movies for hundreds of millions of years. You see the whole pattern spinning around. And meanwhile, remember that these ovals, the individual ovals are what stars and gas clouds are moving on. And they are moving around at a different rate than the global angular pattern speed. It's going to depend on how far you are from the center. But in other words, for some of these orbits, you'll be moving around faster than the global angular pattern speed. And what does that mean? That means you're going to catch up to the spiral arm, move through it, and then move out of it. So it's like, hi, I'm the sun, and so in this frame of reference, where the spiral arms are stationary, here I am. I'm not in a spiral. Oh, I'm in a spiral arm now. Ooh, I'm part of a spiral arm. Oh no, I'm leaving it behind now. I'm not in a spiral arm anymore. I kind of like being in a spiral arm. I wonder if I'll ever be in one again. Ooh, wait. I'm starting to feel like maybe I will. Oh, I'm in a spiral arm again, and so on and so forth. Okay. So now, do what I just did, except I'm spinning it around, right? So I'm spinning it around, and there's little ants crawling on all those little ovals, walking through the spiral arms as the whole thing spins around. If you have a 2-arm spiral, that's what's going on. You can have 4-arm spirals. You can have more complicated patterns than this, but this would be like the simple 2-arm situation. But you can also have situations where there's 4 arms. See the text and figures there. Yes?
So, was there like helicopters versus contractors that you speed up and slow down like you're?
Yeah, that's bullshit.
Okay.
Yeah,
Okay.
so that's sometimes right. And in fact, if you watch the videos that you can get to, if you look at the slides online, he kind of does that. The idea of like a traffic jam, not a good description, to be perfectly honest.
Are they like, if you're moving along, are you changing your speed?
Nope, you're keeping your speed. So really, what's happening is think of a weird road, a weird path like this, where the lanes that cars have to move on behave like this. So why do cars bunch up on this weird road with its funny lanes? It's not because you're speeding up and slowing down, it's because the lanes themselves are converging. Here's 2 cars, we're far apart now, we're driving at the same speed, we're far apart now, okay? Now the one on the inside track is going to be catching up to him passing because he's got less far to go. Here's 2 cars, wait a minute, we're getting closer together because our lanes are forcing us closer together. And now we're spreading apart because our lanes are diverging now. So it's really about the lanes, if you will, about the orbits that things are following. The bunching happens because the orbits get closer together in the spiral arms and further away outside of them. That's how the picture is. Yes?
I thought that the reason why galaxies don't move, or move don't move at the same rate and everywhere was because of dark matter.
Okay, so dark matter is definitely going to play a role in the details here. And we'll tell that story. But if you look at a photograph of a galaxy, it looks like mass is concentrated towards the center. And really, if you look this doesn't show how much it is. In other words, when you look at photos of galaxies, they tend to overexpose the nucleus, the central region, in order to bring out more detail in the outer regions. But if you just look at a galaxy through binoculars or through a telescope, you don't see all that glorious detail because your eyes can't show it, they're not sensitive enough. But like if, for example, you look at the Andromeda galaxy through binoculars, you definitely see that the nucleus is much brighter than the outer regions are. And so from that standpoint, it looks like, wow, the stars and gas and dust are really concentrated towards the center. And in that case, what would happen is that the orbital speeds would fall off with distance from the center. Well, as Vera Rubin showed, everything orbits at about the same rate, the same orbital speed, and that's inferred to be because of the existence of unseen dark matter. And you'll also do a homework problem where you will use that to, along with Gauss's law again for gravity, estimate the density distribution of dark matter, how it's distributed with distance from the center. Because you have the tools to do that. And the one thing to realize is that even though everything is moving at the same speed, it's still true you have the winding problem. Because stuff closer to the center doesn't have as far to travel. It's not that the angular rate is the same for everything. It's how fast, excuse me, it's how many meters per second it's going, not how many radians per second it's going. That is the same as you get further and further away from the center. That angular rate of going around the center is diminishing as you get further because you simply have further to go when you're further from the center. Does that make sense?
Yeah.
Yep. Do you have a question?
I've seen some galaxies where like the arms are a lot more like spread apart,
Mm-hmm.
kind of. We can still like draw a circle on that, and like there's still stars going through that big dead area that looks like there's nothing.
Yeah, in other words, you know, this is one particular orientation of the ovals, if you will. But you can do it differently so that you can get 4 arms, and also you know, this is corresponding to a certain rate, if you will, at which the semi-major axes are being misaligned with one another. And if you made that more gentle, it would make the spiral arms less tightly wound as a result of that.
But there's like still like tons of stars in between those arms that maybe
Yeah.
aren't visible.
Now, there's plenty of stars in between, right? So in other words, there's plenty of stars that are in between parts. And if you photograph excuse me, a galaxy, just like, you know, in white light, so to speak, you know, just like, you know, pretty much let in all visible wavelengths, then you see the spiral arms very distinctly because those O and B stars are freaking bright. And so you see the blue spiral arms. But if you put a red filter in front of your camera and photograph it, the red filter largely blocks the blue light from the O and B type stars, and it's a lot harder to see the spiral arms because of that. You can see through a red filter that overall the stars are fairly evenly distributed around the galaxy. There's still concentration in the spiral arms because of this piling up effect, but the luminosity of those blue stars really delineates it and exaggerates its appearance, essentially. Yes?
What causes the like orientations of the orbits to misalign? Like, what determines like the pattern?
So yeah, so it's because of instabilities in the disk, such that if you and often it can be because of close encounters of galaxies. If you perturb, so if you go here and you perturb this a little bit, like another galaxy comes by and disturbs the orbits of stars here, you can show that that grows in amplitude and that it naturally produces something that looks like this. And so I can't give a simple, like, intuitive answer to exactly how that arises, but I can point you to my lecture notes and to the book where they go through the math of, and it's pretty cool actually, they go through the math and show that you actually do expect this. Yeah. It's pretty fun, but we don't have time for it. Sad. Yeah. But a very good question because it is something, if you really want to understand the details. Okay. Can I go to the next slide? Here is a colorful illustration of what we're getting at here. So here again, the orbits with systematic misaligning of the major axes. And so I talked about stars passing through spiral arms because they're orbiting the galaxy at a different rate than the spiral arms are, right? The whole pattern goes around the center of the galaxy. And so why do we get enhanced star formation in the spiral arms? Because the material is more concentrated there. Because here's a bunch of giant molecular clouds. Boom-de-dum-de-dum. I'm a giant molecular cloud, minding my own business. Ooh, there's an equilibrium between pressure and gravity. Ooh, hey, what would... Poof. They start bumping into one another because they're on different orbits that are converging. And remember that we need something to set off star formation to tip the balance between the outward push of pressure and the inward pull of gravity. We need something to tip the balance. Collisions between giant molecular clouds can compress parts of them and tip that balance, make gravity stronger than pressure, and once that happens, you get star formation beginning to occur. So these molecular clouds bump into one another more when you're in spiral arms because things are concentrating there, just because their orbits are bringing them together at those locations. So gas clouds, following the same orbits of stars, become compressed as they enter spiral arms because they're bumping into their neighbors. Compression of clouds causes them to form new stars, including the blue, high-mass, hot young stars that give spiral arms their distinctive hue. But remember, let's see, how long does an O star live, roughly? live 1 billion years? Does it live 500 million years? Does it live a few million years? Yeah, it lives a few million years. Wait, how long does the sun take to go once around the galaxy? Like 225 million years. So how long ago, different thing, how long ago did the dinosaurs, the non-avian dinosaurs go extinct?
Around that time.
Nope, it was more recent than that. Remember? It's about 65 million years ago. So, in other words, the sun was around a third of the way around the galaxy from where it is now. 1 or 3.5 or something like that. From where it is now, when the dinosaurs, the non-avian dinosaurs became extinct. In any case, let's see, how long is the sun going to be on the main sequence? Like 10 billion years, it's about halfway done, a little bit less than that. So, low mass stars, born in the spiral arms, live long enough to leave the spiral arm and then go into another spiral arm, etc. But if you're an O-type star, you're born in the spiral arm, let's say you're out in the region where the sun is, it's going to take you, if you could live, 225 million years to go once around the center of the galaxy. But if you live 10 million years, do you get very far around the center of the galaxy before you blow up good? No, you do not. So the O-type stars never make it out of the spiral arms that they were born in. And so they're always concentrated in spiral arms. They don't live long enough to leave the spiral arms where they were born before they just explode as supernovae and go away. So blue stars die away long before they complete one orbit, and thus tend to remain close to the spiral arms where they were born, but red and yellow low-mass stars, like the sun, populate the entire disk because they have longer lives, and survive for many, many orbits. So that's the big picture. Blue stars are concentrated in the spiral arms because they don't live long enough to leave their hometowns, basically, right? They're all a bunch of homebodies that stick around their hometowns. Whereas the sun, stars like that, it's like, I want to see Paris, you know? And so they leave the village where they were born, so to speak. Because stars have personalities and desires and so on and so forth. I think I better take a break right now. Break time. Onwards and upwards. Let's take a tour of galaxies, shall we? But first, let's talk about the star-gas-star cycle as the cosmic perspective, the book that I use in intro astronomy calls it. But you know, it's good name for it. Star-gas-star cycle. So, we've said some of this before, right? So there is what we call the age-metallicity relation for stars. Namely, the younger a star is, then on average, the higher its metallicity would be. Why is that? Why should old stars have low metallicities and young stars have high metallicities? Point number one, where do metals come from? I heard things. I don't know what I heard. Just, yeah. Yeah. Where are they born? Where are metals? Where do metals? After the Big Bang, were there metals? No. What was there in the universe after the Big Bang in terms of ordinary hydrogen and helium, right? So where did the metals come from?
From stars.
From stars, right? Stellar cores, right? Nuclear fusion, right? Are stellar cores Vegas? What's in the core stays in the core? No. When stars die, some of their material that they've processed in their cores gets ejected into space and becomes part of the interstellar medium. And so over time, the interstellar medium becomes more and more enriched in metals from earlier generations of stars that lived and died and ejected material into the ISM. And so Old stars, born long ago, were born from material that didn't have as much time to build up metals in it as young stars do. So younger stars, born later in the history of the galaxy, tend to have higher metallicities than old stars born earlier in the history of the galaxy, simply because over time the ISM gets more and more enriched in metals. Question?
So tend to have is just because they're in an environment that had a lot of metals already?
So tend to have would be, yeah, just on average, the interstellar medium becomes more enriched in metals over time. There's variations from place to place, but there's an overall trend that younger stars have higher metallicities because they're born from material that had longer to be enriched in metals by prior generations of stars. Yep. And the sun's metallicity in terms of like the mass fraction of not hydrogen, not helium, the mass fraction of metals is around 2%. The most, there are some very metal-rich stars that can, be significantly higher than that, but 4% is a very high metallicity. And halo stars can be much lower than that. Can be much lower than the sun's metallicity, like 0.1%. I think you can even get that low. So there's a hypothetical population Roman numeral 3 of stars, which would be essentially pure hydrogen and helium, no metals. You could have a little lithium because the Big Bang made a little bit of lithium, things like that. But hypothetically, there should be a generation of stars that had no metals in them. We call that population 3. We have never seen such a star. We've never taken a spectrum of a star and said, wow, all I see is hydrogen and helium lines. But you remember why? We did mention this. We now understand why this would be. So, anybody remember why, or is that it?
It was because they died off already, no?
They died off. And why did they die off? Because they were all very
hot and very large.
Yeah, they were all massive. They were all high mass, very short-lived stars. And that's because remember that molecular clouds are cooled by molecules, by dipolar molecules that can rotate and vibrate in the quantum way and give off radiation and cool the cloud and thereby reduce the gene's mass, reduce the mass a cloud needs to form a star. But clouds that only have hydrogen molecules in them, molecular hydrogen, can't do that. Molecular hydrogen is not a good radiator of long-wave infrared and radio waves, and that's because of a property of a hydrogen molecule. It's got two hydrogens, right? Is either end, does that going to have a dipole moment? Is a hydrogen molecule going to have a dipole moment? No, because both hydrogens, it's symmetric, so there's no reason for the electron cloud of the molecule to be more concentrated on either one of the hydrogens. So they don't have a dipole moment, and you can show that a rotating or vibrating dipole gives off electromagnetic waves, but these molecules, hydrogen molecules, are not dipolar. And so the essentially pure hydrogen and pure helium clouds that would have made the very first generation of stars were not able to cool down by radiation emitted by molecules. So they stayed hotter, which made their genes' masses larger, kept pressure higher, so you needed much more mass to overcome that. You needed more massive cloud to overcome that. So now we understand it, that the first generations of stars should all have been very massive and very short-lived. None of them are alive anymore for that reason. They're all gone. They blew up shortly after they formed. Did you have a question? Or no? Yeah, okay, yeah. Whereas, for example, one molecule that's very good at cooling off giant molecular clouds is carbon monoxide, CO. Don't read the stuff, but it's fairly common in clouds, not nearly as common as hydrogen for sure, but as metals go, carbon and oxygen are amongst the most abundant types of atoms in the universe. Very least, much less than hydrogen and helium, but as metals go, they're quite abundant. So CO is a relatively abundant molecule. So if I've got CO, what's better at attracting electrons, carbon or oxygen? Which one's more electronegative, as chemists would say? So it turns out it's oxygen is more electronegative. Unless I'm missing something, I could be wrong, I ain't a chemist, maybe
I was just thinking how many electrons they have.
Oh, it's not a matter of that, it's a matter of how good they are at attracting electrons. So CO molecules are, in any case, yeah, I'm pretty sure that oxygen is more electronegative. And I think it's because, I better shut up because I was saying something stupid chemistry-wise. But anyway, CO molecules are polar molecules. One end's negative, one end's positive. And when they rotate or vibrate, that means that they're going to be giving off radiation. And so CO and other molecules like that cool interstellar clouds today, and a cooler cloud has less pressure, and so a smaller mass can create a star in such clouds. And but the first generation of stars would have all been very massive because of the lack of that effect. Anyway, this summarizes the idea, the big picture, that the interstellar medium and stars are in a feedback loop where the composition of the interstellar medium gets enriched in metals over time. So, interstellar gas clouds fill the galactic disk. Gas in the disk gradually cools and forms molecules, so we get molecular clouds. Gravity makes stars from molecular hydrogen gas. In the regions of giant molecular clouds, you get star formation. Fusion in the course of stars makes new elements from hydrogen and beyond, right? In other words, a high mass star that will then fuse helium and then carbon and so on and so forth. The sun will fuse hydrogen. Will the sun fuse helium someday? Yes, the sun will fuse helium someday. Will it ever fuse carbon? No, it will not. But higher mass stars go past helium fusion and fuse carbon and so on and so forth. You get the onion, right, that's fusing silicon and sulfur into iron. Can iron fuse? Not and give off energy, no, so it doesn't serve as a nuclear fuel, so the star's going to really look good as a supernova. Fusion in the course of stars makes new elements from hydrogen. Supernovae and stellar winds return gas and new elements to interstellar space. Returning gas cools and then blends into atomic hydrogen clouds. You get these hot bubbles that are blown by supernova blast waves. And in other words, the point is that star formation and death are constantly enriching the interstellar medium. And so over time it becomes richer in metals, so newer generations of stars tend to have higher metallicities in them than earlier generations did. Yes?
If the cycle of fusion ends with iron, how do we get to the higher mass elements?
Right, so two ways. One is that there are endothermic reactions. There are endothermic reactions, right, that require energy. In a supernova shock wave, everything's being slammed around at such high speeds because of the high temperature that you do get some endothermic reactions in there that produce some post-iron elements. And so supernova shock waves are one source. You can also get some production just inside the milieu of fusion reactions that are happening in stars. You can capture, there's neutron capture reactions, which is relatively easy to do because there's no Coulomb barrier. And so again, it's taking energy for making these higher mass elements, but it can be done. And then remember, merging neutron stars is a significant source of elements that are past iron. And again, yeah, it's taking energy to do it, but there's a lot of energy available in a pair of merging neutron stars. There's a lot of energy available in a supernova shockwave. So it's not that those reactions can't happen, it's that they can't serve as a sustainable source of core fusion. But they can happen in shockwaves, neutron star lasers and stuff. Yep. Okay? So do understand that big picture, the age metallicity relation, that younger stars tend to have higher metallicity than older stars because of the enrichment of the interstellar medium over time by generations of stars. Okay, let's have a rogues gallery here of various galaxies, if you will, a gallery of galaxies. So here is M101, a face-on spiral galaxy. It is if my memory serves, the most, for the Hubble Space Telescope, I think it's the most distant galaxy in which we've been able to observe Cepheid variables, which we'll have more to say about, as a matter of fact. And so it's a classic so-called grand design spiral galaxy where the pinwheel is very well organized. Here is NGC 4114. So you know M stands for Messier. NGC, remember what that stands for?
New General Catalog.
The New General Catalog, yes. When was it new?
1800.
It was 1885, I think it was. Maybe 1895. I think it was 1885. Anyway, in the late 1800s, it was new, and we still call it that. The New General Catalog. The formerly, which is the FNGC. The formerly new, right? Or maybe it's the OGC. No, we just still call it NGC. NGC 4414, a spiral galaxy whose disk is somewhat tilted to our line of sight. This is a so-called flocculent spiral rather than grand design spiral. Flocculent means basically woolly. Woolly, as in like wool, you like take a bunch of wool or cotton and go. So it's called flocculent because it kind of looks like you did something to a bunch of wool or cotton like that. And these are thought to form rather than distinctive density waves like that. These seem to be a result of self-sustaining star formation, where if you do have, you may recall, maybe you don't, we're talking about star formation, you can have, because of winds and supernova shockwaves from massive stars that form in a region, those winds and shockwave and supernova blast waves, shockwaves, can compress the surrounding interstellar medium and create more star formation. So once star formation begins, it can be self-sustaining because winds from hot stars and supernovae can induce new star formation. So imagine that you had a little caterpillar of star formation that happened to form here. Here's a little caterpillar. Here's my finger here. Well, let's see. If this is a blob of stars, and it wouldn't be as big as this, is it this side or that side that as we go around the galaxy we'll get further, because it's going to be carried around the galaxy. Which side is going around the center in the least amount of time? This side, right? This side is. And so there's going to be a natural tendency for those to get kind of systematically tilted because the stuff closer to the center goes around the center in less time. It's all moving about the same speed, but goes around the center in less time. So imagine a lot of regions of self-sustaining star formation, and there'll be this tendency for them to systematically tilt towards the center as they go around the galaxy. And so you can get this pattern like this where you can see a swirl to it because of that. It's all swirly because of that. And And so flocculent spirals seem to be dominated by self-sustaining star formation, then being, kind of mixed up by the rotation of the galaxy, as opposed to distinctive density waves that you have in a grand design spiral like this one. And here we have NGC 891, a spiral galaxy seen nearly edge on. Note the central streak of dust associated with the disk. That's typical that you'll see like dust like that within the disk. Because remember that the dust is good at scattering light, and so it's just obscuring the stuff behind it as a result of that. What questions do you have about any of this goodness? Push the magic button. That's a question for you. Okay. Here is M87. This is the galaxy where they used the Event Horizon Telescope to image the accretion disk around the black hole in its center. So there it is, except you can't see it. There it is, really, really tiny. That's where it is. You needed a high resolution Event Horizon Telescope to actually resolve that. M87, a giant elliptical galaxy in the Virgo cluster, is one of the most massive galaxies in the universe. The region shown is more than 300,000 light years across. If I look at these cute little spiral galaxies in its vicinity that are part of the cluster, our Milky Way is a quote-unquote giant spiral. It's bigger than most spiral galaxies are, but it's dwarfed by elliptical galaxies. There are elliptical galaxies that can be like 1 million light years across or more, much larger than our Milky Way galaxy is. And you see all these fuzz patches? Those little fuzz patches there, can you guess what those are?
Not stars.
What's that?
Are they stars or not stars?
No, they're not stars, but they're big collections of stars. They're globular clusters. Yeah, they're globular clusters. There are many, many globular clusters surrounding M87. So in other words, we have both spiral galaxies like ours and elliptical galaxies. Is there a lot of star formation in this elliptical galaxy? There is not. How do you know? It's red, right? If there were a lot of star formation, there would be hot young O and B stars giving off lots of blue light. Instead, it's red, so this light must be dominated by what kinds of stars again? Just like in the bulge of our galaxy? Red giants, yeah, red giants. The bulge of a spiral galaxy is kind of like a miniature version of an elliptical galaxy. In an elliptical galaxy, it doesn't have a lot of angular momentum for having that much mass, unlike a spiral galaxy. It's like a giant halo, if you will. The stars are moving every which way instead of systematically around the center. And so, sure, it's got some net angular momentum, but compared to the ratio of angular momentum to mass is much smaller than it is for a spiral galaxy. And notice here's another elliptical galaxy. It's just not a giant one. It's elliptical. Ellipticals have a huge variety in their sizes. Here's a dwarf elliptical, Leo 1, because it's in the constellation Leo, it's behind those stars, is one of at least a dozen cute little dwarf elliptical galaxies in our so-called local group of galaxies, which consists of the Milky Way, the Andromeda Galaxy, which is about 2.5 million light years away, and M33, which is a spiral galaxy that's smaller than ours. Ours is 100,000 light years across. M33 is about 40,000 light years across, so significantly smaller than the Milky Way. The Andromeda Galaxy is about 150,000 light years across, so it's the largest member of the local group. We're number 2. We're number 2. But as spirals go, the Milky Way is considered a giant spiral. It's larger than most. But the local group also has a lot of so-called dwarf ellipticals in them, which, as you can see, are much less densely populated they're much smaller than something like M87. It's only about 2,500 light years across. Then we have the Large Magellanic Cloud, which is a satellite galaxy of our own Milky Way galaxy. And it's about 30,000 light years across. It's a so-called irregular galaxy because it's neither spiral nor elliptical. It's a bit of a hot mess is what it comes down to. It maybe has some hints of like a bar in it, like maybe it used to be a small spiral galaxy, but it has passed near the Milky Way galaxy and it has been distorted by that. But it's a satellite of our own galaxy. It's orbiting us. Here's the small Magellanic Cloud, which is also a companion to the Milky Way, about 18,000 light years across. Are these galaxies sites of active star formation? They are. Look at that. What's that? It's pink, so that must be. Yeah, it's an ionization. It's a what do you got? Emission nebula or H2 region. This, in fact, is called the Tarantula Nebula. It's a very large H2 region. Now, interestingly, the metallicities of the stars in the Magellanic Clouds is lower than that in the Milky Way, even though there's a lot of star formation here, because if a supernova blows up in one of the Magellanic Clouds, the galaxy of the gravity is weaker than the Milky Way's gravity. And so the material can just fly off in intergalactic space instead of being recycled in future generations of stars. And so they don't get as enriched in much in metals as larger spirals do. Here's NGC 1427A, irregular galaxy with scattered patches of star formation, about 50,000 light years across. And then there's a spiral galaxy way off in the background. So this is the so-called tuning fork diagram that Edwin Hubble produced to classify galaxies, called tuning fork diagram because it kind of looks like a tuning fork. And when Hubble created this, he imagined that it might be an evolutionary sequence, kind of like, remember, astronomers used to think that stars moved down the main sequence as they aged, that they started out as hot O stars, and as they quote-unquote lost energy, they cooled off to be cool red M stars. Is that what actually happens? Emphatically not. A star pretty much, it spends most of its life on the main sequence, moving just a little bit on the HR diagram, and then it moves up into other portions of the HR diagram. There's nothing about moving down the main sequence or anything like that for any individual star. So Hubble imagined that this might be an evolutionary sequence. It is not. I'll just say that. It is not. The Milky Way, if it doesn't interact with anything, is just going to stay a spiral, except it's going to collide with the Andromeda Galaxy and form an elliptical galaxy. But if it stayed isolated, it would just stay a spiral. It wouldn't evolve into an elliptical or vice versa. So, certainly wouldn't be, well, if they were going to do that, I wouldn't even say. She might start thinking these things. But anyway, so we'll start with the ellipticals, with their overall color is what? Reddish, right? So, star formation? Nope, they're not sites of active star formation. Star formation must have shut off long ago in them. They presumably formed lots of stars early, used up all their gas and dust, and then that was it, as far as that's concerned. They are categorized with, you call it capital E to mean elliptical, and in a number between 0 and 7. And the number is based on how much it differs from looking like a circle. In other words, an E0 looks like a sphere, and E5 here, it's elongated, And so the higher the number, the more elongated in appearance the galaxy is. Now, it is just based on how it looks from Earth. We can't tell the true shape of the galaxy because suppose that I have an elliptical galaxy that's like my hands here, you know, it's like kind of football shaped. Is this a sphere? No, but if the long axis is pointing towards you, it would look like it had a circular outline. And so the classification isn't based on the true shape of the galaxy, which we generally can't tell. It's just based on how it looks from Earth, as far as that's concerned. Okay? And then we get what we call lenticular galaxies. A lenticular galaxy is one that has a disk, but are these blue? No, they're reddish in color. So it's got a disk, like a spiral, like the Milky Way, but it doesn't have spiral arms, and it's not a site of active star formation because its disk doesn't have a significant amount of an interstellar medium, gas and dust. There's nothing to form stars from. So they on some level, seem intermediate between spirals and ellipticals. And notice this one's called S0. The 0 means that it's lenticular, that it's not a classic spiral galaxy with blue arms and all that sort of thing. And then B stands for bar. Capital B stands for barred. So this is an unbarred one, and this is a barred one. In other words, the central bulge has a bar across it. Then when it gets to the spirals, we got for the so-called normal spirals, although there are plenty of spirals that are barred spirals, the so-called normal spirals, they don't have a bar sticking out of the nucleus, out of the central bulge. They just got spiral arms. But we notice something systematic. So first of all, the small letter is based on how tightly wound the spiral arms are. A is tightly wound spiral arms. C is loosely wound spiral arms. B is somewhere in between. Personally, I like the SC galaxies. I think they're the prettiest. I like that loose pinwheel structure like that. But notice that the nucleus of this SC galaxy is smaller compared to the disk than it is in the SB, which is smaller than it is in the SA. So those things go together. SA galaxies have large bulges and tightly wound spiral arms. SC galaxies have small bulges in the center, small nuclei, and loosely wound spiral arms, and SBs are in between. Meanwhile, we've got bar spirals, so that's capital S, capital B, and then an A, a B, or a C, and that refers to the spiral arms appearing to be attached to a bar that goes through the center of the galaxy. For a long time, we thought that the Milky Way was an SB galaxy, but now further observations where we can peer in towards the central regions have shown, no, there's a population of stars that appears to be arranged in the form of a bar. So we now think that our galaxy is SBB, that if you saw it from the outside, you'd see a central bar. So pretty cool. So the Andromedans would see something of a bar if they looked at the Milky Way, whereas the Andromeda galaxy does not have a bar. And I think it's fairly edge on, so it's a little hard to tell, but now I can't remember. I think it's an SA, or maybe even an SAB, because they do that. It's like, you can say S little a little b if it's kind of in between partial credit, so to speak, you know. Anyway, that's the general overview of how Hubble classified galaxies. When I was in college, I took an artificial intelligence class. Believe it or not, we had it back then. Not quite what we have today. But I wrote a quote-unquote expert system that would take photos of galaxies and classify them as to whether they were SA, SP, or whatever. So I don't remember how well it did, so I'll just tell myself it worked. Okay, so this is a diagram that's kind of like an HR diagram, excuse me, for galaxies. So, because on the y-axis we've got the luminosity, just like the y-axis is luminosity of an HR diagram, and the x-axis is color. So you could do something like the B minus V color index. Photograph the galaxy through a B filter, and the B filter, find the magnitudes, subtract, make B minus V. So of course, for stars, you get a main sequence, right? And then, most stars lie along a main sequence for stars. Here, the luminosity units are very different for stars because galaxies contain millions to billions of stars, and so the luminosities are in terms of, here's 100 million times more luminous than the sun, 1 billion times, 10 billion times, 100 billion times more luminous than the sun. The question would be, if you do that for galaxies, is it just random dots that you would get, or is there anything systematic? And as you can see, you get something systematic. There's concentrations within the diagram. And so we talk about the red sequence and the blue cloud. Not literally a cloud in space, it's a cloud on the diagram. Plotting many, many galaxies on here. And so large blue-white galaxies have active star formation. They'd be up here. They're large, so they have a lot of luminosity. They're pretty bluish in color. Small blue galaxies are even more dominated by the light of the young stars, hot O&D type stars within them. So here's young stars producing most of the light from small blue galaxies, so they're dimmer, but also very blue. Smaller galaxies without star formation tend to be companions of larger galaxies. So here's a dwarf elliptical. It looks like it might belong to the Andromeda galaxy because there's a dwarf elliptical. The Andromeda galaxy has 2 dwarf ellipticals orbiting it that you can readily see in photographs of it. Whereas the Milky Way, the most prominent satellites are those 2 irregular galaxies, the Large and Small Magellanic Clouds. Anyway, they're going to be red because they don't have active star formation in them. They're going to be dim-ish because they're not large, essentially. The largest galaxies are giant ellipticals. This one's M87, show up way up here without much star formation. So the red sequence is going to be large elliptical galaxies. The point is that it ain't random, right? You could imagine there could be just like dots everywhere on the picture, that you could have very bright red and very bright blue galaxies. You can see, though, the brightest galaxies are in the red sequence, for example. Those giant ellipticals are more luminous than even the most luminous spirals. So, of course, this is the sort of thing where, if you're trying to make a simulation of the universe, and you look at the galaxies that you're simulating, you've done a good job if you made a plot and it looks something like this. If it doesn't, well, you got some work to do. Right? Okay? What questions do you have? Okay? Let's talk about standard candles. I love that name. Standard candles, it's a fanciful name. Somebody should study these things, right?
Wow, somebody should.
Somebody should, yes. A standard candle is an astronomical object with an already known luminosity. In other words, if you just pick some random star and you want to know what its luminosity is, you need to be able to determine how far away it is and measure its apparent brightness in order to calculate what its luminosity is from its distance and apparent brightness. And so you need to be able to do something like measure its parallax, measure its apparent magnitude, and turn that into its absolute magnitude, which is a measure of its true luminosity. But what if there are some types of objects where you could be confident that they all had the same luminosity, and then your job would just be observe nearby ones and deduce what their luminosity is from their apparent brightnesses and their measured distances. And then you could say, okay, well, I know how luminous this type of star is because I've measured nearby ones. Oh, if it's so luminous that I can see them in distant galaxies, why, I could say, okay, here's this distant galaxy with this type of star in it. I know how luminous that star is. The galaxy, you can't use parallax to find distances to galaxies. They're way too far away from that. But if it's got a standard candle in it, a star or other object whose luminosity you know, you can measure the apparent brightness, take the known luminosity, and turn that to the distance to the galaxy. You can determine distances that way. That's the big picture here. A standard candle, in other words, it's a standard candle because, you know, the Acme Candle Manufacturing Company, here's model 705 of their candles, and they all burn with the same brightness. That's why we call them standard candles, quote unquote. A standard candle is an astronomical object with an already known luminosity, comparing its apparent brightness to its luminosity, its known luminosity, tells us its distance via the inverse square law for light, as expressed by the magnitude-distance relation. Remember that the magnitude-distance formula is really the inverse square law written in terms of magnitudes. So what do we call, what does big M represent here? That's the absolute magnitude, right? Which is the apparent magnitude. That's what little m is what we measure. What's the definition of the absolute magnitude? It's the apparent magnitude as seen from a standard distance of 10 parsecs. Yeah, 10 parsecs, right? So little m minus big M is 5 times the logarithm base 10 of the distance in parsecs minus 5, right? So what you really do, we typically write it, we often write it like this, you really invert this to solve for d, right? So if you measure little m and you know big M because it's a standard candle, you can calculate what d is. You can figure out what the distance is. That's why these things are so useful. Okay? What questions do you have? Okay, well let's talk about a particularly useful type of standard candle, namely Cepheid variable stars. Yes. So, you may recall that it turns out that high mass stars move horizontally back and forth. They go a wandering across the upper part of the HR diagram after they leave the main sequence when they've used up all their core hydrogen. They wander back and forth. Unlike a low mass star, right? Remember that a low mass star like the sun climbs the red giant branch, switches to the horizontal branch, climbs the asymptotic giant branch, and then becomes a white dwarf, right? But these high mass stars don't have a tight coupling between what's happening on the inside and what you see on the outside. Instead, models indicate that they wander back and forth. How much is the luminosity changing? Is it changing much? No, right? Because a horizontal line is constant luminosity. So what's changing is the size and surface temperature of the star. They wander back and forth across the top of the HR diagram, and it turns out that there is this region called the instability strip where they are unstable to pulsations. Why, I would say that a star is a balance between the inward pull of gravity and the outward push of pressure. If a star is in equilibrium, then it keeps essentially a constant radius and luminosity. Now, is the sun on the main sequence in perfect equilibrium? No, you may recall that as it's fusing hydrogen into helium in the core, the fusion rate is slowly increasing because of the fact that the number of particles in the core is always diminishing. And as a result of that, because 4 hydrogens make 1 helium, and all that matters is the number of particles when it comes to the pressure. It's NKT, right? For an ideal gas law, pressure is NKT, where N is the number of particles per cubic meter. So if you're building helium nuclei out of hydrogen, you're systematically reducing the number of particles there. And it turns out that what's happening then is that pressure is a little bit weaker than gravity in the sun's core, so it's slowly contracting. Virial theorem says it's slowly heating up, and that's increasing the fusion rate, so the sun is slowly brightening while it's on the main sequence, but that's over very, very long time scales. But these stars, the ones that are in the instability strip, we don't have time to go into details here. The authors of your textbook study variable stars, that's their specialty. So read chapter 14 about variable stars if you want to read all about this. But what I want you to understand is that in these stars, sometimes pressure is stronger than gravity, sometimes gravity is stronger than pressure, and they pulsate as a result of that. They systematically pulsate because they go through cycles where gravity's winning, pressure's winning, gravity's winning, pressure's winning. And so they pulsate as a result of that. And it turns out it's when they are in the instability strip that they are unstable to pulsation. Okay? Questions? So, this is of fundamental importance. There's a class of variable stars called the Cepheids because the prototype is the star Delta Cephei. Remember that? So it's not always correct, but the brightest star in a constellation is called what plus the Latin genitive of the constellation's name? What are the letters of the alphabet in your Greek? Alpha, right? The second brightest is? The third brightest is? The fourth brightest is? Ding, 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 ding. Fourth brightest star in the constellation Cepheus, on average. Delta Cephei, I say average because it varies in its brightness. By the way, and I hope you've known this before, and if it didn't, you can do one of these today. Where does the word alphabet come from? Yeah. What's the first letter? Alpha. What's the second letter? Beta. The alphabet's the alpha beta. Literally, that's where the word comes from. So if you never knew that before, right? Okay. Here is a plot, which is actually duplicated, but if you can do this, right, and just keep taking it over time. Here's the brightness and apparent magnitude of the V magnitude, apparent V magnitude of Delta Cephei over time. Do you remember what's the dimmest your eye can see in the magnitude scale? 6, yeah. So is this star visible to the naked eye? Yes, because smaller magnitudes are brighter. It wouldn't have been named Delta Cephei if it weren't a star that you can see with the naked eye. All the ones that have the Greek letter designations are naked eye stars. But notice it's varying between about 3.5 and 4.5 magnitudes. Magnitude on magnitude scale. Let's see, 1 magnitude is a factor of what in brightness, roughly? Do you remember? Oh my God, he's asking us all these questions. 1 magnitude of brightness difference is about what factor of brightness difference? It's the 5th root of 100, which is about what?
2.5?
Yeah, 2.512 is 1 magnitude of brightness difference. This is readily observable with the naked eye. And so you can actually locate the star in the sky. It's easily seen. It's bright enough. And if you systematically observe it from night to night, you can see it getting brighter and dimmer, brighter and dimmer, brighter and dimmer. And in fact, we can observe many, many periods and run Paranzo on it, if you know what that is. There's period analysis software. And through many, many periods of observations, we can be quite precise. Its period is 5.36634 days. You can actually determine it quite precisely. And the point here is that Cepheids are standard candles. We'll come to this next time. But Henrietta Swan Leavitt, what a wonderful name, discovered by studying stars in the SMC, Small Magellanic Cloud, that there is a systematic correlation between the star's oscillation period and its average luminosity. Because all the stars in the Magellanic Clouds are essentially the same distance away from us, their apparent brightnesses are a true measure of their actual luminosities, right? In other words, if one looks brighter than another, it really is more luminous because they're essentially the same distance away, because they're all in the Small Magellanic Cloud. And so as a result of that, because it's much smaller in size compared to its distance from Earth, they're all essentially the same distance away. And so she showed, and as a result is now called Leavitt's law in her honor, that there is a period luminosity relation such that if you can observe a Cepheid variable star and measure its period, why, you can consult this plot and figure out what its luminosity is. Aha! Standard candle. Standard candle. You don't have to use parallax to get its distance. The period tells you its luminosity. This had to be calibrated with nearby Cepheids. But once you got that calibration, you can say, aha, why my Cepheid with a period of 30 days is more than 10,000 times the sun's luminosity, whatever this is, right? 11, 12,000 times or whatever the number is. That's luminous enough to be seen in other galaxies. That's luminous enough to be seen from millions of light years away. Next time we'll tell the story of how Edwin Hubble systematically searched for Cepheid variables in the Andromeda Nebula, because there was a debate whether the spiral nebulae were just gas clouds in our own Milky Way, or they were separate cities of stars. And some astronomers thought that the Milky Way was the galaxy, that there was one star system just surrounded by infinite empty space. And others thought, no, Immanuel Kant argued that, the philosopher, argued that they're island universes, separate systems of stars, and that our galaxy is just one of many. There was a big debate about this in the early 20th century. Edwin Hubble solved the debate by making use of Leavitt's law to show that a Cepheid variable he discovered in the Andromeda galaxy was too far away to be part of the Milky Way galaxy, and therefore our galaxy is just one of many galaxies. So we'll tell the story more fully next time. That's where we're going to start. Yeah, it would be, and then I've also, but, so, because you wanted to talk to me too, right?
Yeah, but I don't think we need to talk about anything, the program is running, so.
Yeah, if there's nothing to report, everything's running. Well, there is something that I wanted to point out. We could do that tomorrow, but it's not, yeah, it's no emergency. Yeah, so, okay, yeah. Yeah, just come in lab again tomorrow and I'll tell you about it.